Hello and welcome to this podcast for Electropages. I'm your host, Robin Mitchell. Today we've got a very interesting guest to talk about some new and emerging technologies. So just before we jump into all of that, tell the audience who you are, what you do and what you like to do in your free time.
Hey there, Robin. So my name's Paul Williamson. I am the Senior Vice President and General Manager of IoT at ARM. So I look after, and my team work with me to define the compute that is going into about 20 billion devices around the world every year. And, you know, from a personal level, when I'm not spending my time on that project outside the office, I have two young boys and I spend my time. My eldest is really into some of the things I see in your background, whether it be 3D printing or playing with Raspberry Pis. And my youngest is a very keen mountain biker. So I end up chasing him around courses I probably shouldn't, doing myself injuries as I'm far too old to be doing it, but it's still a lot of fun. So it keeps me
Absolutely. That's absolutely fantastic. And I would just like to put out there that I've got my own one on the way, my first one in September. So when that comes, so I'm quite happy to sort of get this out there and do it, because I've got lots and lots of plans for this child. He's going to be an engineer. He's going to love what I love. There's going to be no negotiation whatsoever.
Oh, well, there you go. I don't know that I've pushed it so much as it was quite organic, but nonetheless, I seem to have at least one on the computer science track, which is
that's good, isn't it?
Not a bad thing for the world.
Absolutely. And I kind of feel like that you push your children towards ARM products more than you would maybe other CPU architectures.
Well, certainly they got access to play with lots of fun stuff. I'm also fortunate to be on the board of Arduino. And so, you know, whether it be, you know, little robots or like the Alvic kit or the just plugging things into Unos at an early stage, they've very much been engaged with ARM-based tech in all of those little projects, whether they know it or not. So, it's been great.
Brilliant. In fact, actually, on the Electromaker side of things, we actually recently did a video of the world's smallest line-following robot using TI's part, which was an ARM core anyway. So that might be something they might be interested in that.
They might.
Anyway.
Yeah, very good.
So ARM, a worldwide company that everybody knows, x86, RISC-V, ARM. ARM is the one that everyone's talking about these days. And personally, for me, I have a bit of a sort of a loving sort of history with ARM, because for me, I know from its origins when, you know, Chris Curry was part of Sinclair Radionics, which became Sinclair Computers, broke apart, did their own thing in in Acorn, and then they built the ARM sort of architecture. And it's quite impressive to see how this small British company developed this sort of reduced instruction set CPU and made it into what is effectively a multi-billion-dollar company that's responsible for probably most devices around the planet. But what I'm interested in is how did ARM actually get into the IoT industry in the first place?
Yeah, that's interesting. So, yeah, you're right. The history is fascinating. And we recently had an event here in the building here I'm based in, here in Cambridge at our headquarters, where the original founders from 40 years ago came together and did a little event on stage and talked about the sort of, I suppose, the origin story, if you like, for the ARM business. And it is fascinating that that was fundamentally about building using this RISC architecture, and having learned about it in academia and sort of seen that was a possibility, the concept that they could, for these Acorn computers, build their own CPU, which at the time, you know, was the preserve of only mega companies like IBM and Intel and others. And so having seen that, they came back and they built something, and they did really pioneer using RISC instruction set architectures to achieve something fundamentally much lower power. And you know, the myth is that when they booted the first device, it was able to run just off the sort of parasitics that were present in the board when they powered it down, and the power supply wasn't even connected for a period. And they sort of realized they had something that was incredibly power efficient. And I think that heritage stayed with the business. So, you know, you get to the sort of the launch of mobile phones, which was when ARM volume really exploded with Nokia devices deploying ARM, and then into the smartphone era. And at that sort of point, you almost get a sort of division in compute need. You get higher and higher performance going into smartphones, but equally you get this, I want smaller and lighter weight, but I want greater software complexity. And you know, the M profile was probably the genesis of getting into these smaller devices at the edge, where people were looking for perhaps the software portability and flexibility that came with a 32-bit RISC architecture, but really we're using a broad range of different provided 8 and 16-bit microcontrollers in that market. So the Cortex-M was kind of ARM's first foray into this space of, well, actually, let's go in with 32-bit and let's enable software portability across different devices. And that really exploded into the sort of general purpose microcontroller market we see out there today. So you see now, Cortex-M from ARM in everything from, these tiniest of little devices, even your TV remote control just for lighting the LED on the front is almost certainly using, a Cortex-M0, a very simple 32-bit microcontroller, through to in IoT, which, really is now a very broad category of devices, the latest visual inspection robots and devices that are using, even the kind of higher performance than you see in the latest smartphones. So it's become a very broad spectrum of compute, but there's some underlying core principles that come from that origin story of low power and software portability that really sort of fit for that market need.
And when it comes to sort of low-powered microcontrollers and the architectures that they run off, there's quite a few out there besides ARM. But a lot of these other businesses, they themselves are turning to ARM. They're starting to drop their own intellectual property cores and stuff. They don't really want to use their own internal cores. They want to just switch over to ARM. Why do you think it is that ARM's been able to do that?
So I think a lot of it is about time in the market and presence, but the biggest part of it is this software ecosystem. So, and I've seen this directly talking to OEMs who are developing devices. There are, I think we say, about 20 million software developers out there who are writing code to target ARM IoT endpoint devices. And if they're writing that code, clearly, they want to be able to preserve that investment in the software or the algorithms and the intellectual property they develop. And they want to deploy it in multiple different products and form factors. And if I look at the microcontroller general purpose space, you see that a catalog vendor is trying to build products that serve a really quite broad range of use cases. Yeah. And so having a consistent developer tool chain and the ability to reuse and deploy your software across those different products is really valuable. And I think the momentum that has grown over a very long period behind ARM and behind those large number of software developers has really cemented ARM as the go-to architecture in IoT devices for developing your code. And we're definitely seeing that evolution continue. I sort of talk about there being sort of three phases that we've seen. In that first phase, it was very much about control code and sort of the general purpose microcontroller just doing switching and decision making.
Yeah.
We've now been through this sort of IoT connectivity phase of adding connectivity and software stack getting much more complex, and you needing Wi-Fi or Bluetooth or Zigbee or all these different standards that you've got to manage all of that software for. And we're now just moving into this AI era of novel AI algorithms running at the edge. And that again is creating this need for even more software complexity. We're having lots of need to take your code and hardware optimize it for lots of different devices is a headache that developers really would rather avoid. And I think that's one of the real strengths to the ARM ecosystem that's carried it so strongly.
And I'm guessing an analogy would be like the Windows operating systems for computers, which is that it gave everybody a platform that everyone could develop on. Code was interchangeable. You didn't have to rewrite the whole thing every time a new update came out. And as a result, everyone's kind of just sort of realizing, well, let's just all jump onto the ARM platform, because now I can code on one platform, transfer it to another, and have no issues with compatibility.
Absolutely. And I think, it is this ecosystem. We do the bits that make that horizontal availability. So we do, we build the IP, and then we ensure that the architecture features are standard across different form factors. And then we make sure that the compilers and the debuggers are built in a way that is familiar depending on the sort of scale of the platform you're building, so that the base ingredients are very stable. And that allows people, the world of IoT is a bit different to the Windows world in that, often people are using their own, sometimes writing what we call bare metal right down at the drivers for the hardware. Sometimes they're taking a real-time operating system, but it's not like one Windows for them all. It's sort of, there's many different, whether it be a automotive specialist operating system or one that's...
I will have to put my hand up there because I myself do everything bare metal. I've got a really bad habit of refusing to use any kind of RTOS whatsoever.
Yeah. And actually, even in that world, ARM does work to make that easier for developers. So we have a program called SimSys that tries to create packs of drivers for the underlying hardware that are consistent between different vendors as well, so that when you, even as a bare metal developer, can more readily address ARM-based products that come from different vendors in the ecosystem. So we're trying to make that platform as scalable for people who want to innovate on top of it as possible.
So when we talk about the IT industry, a lot of people, might think about things like weather station sensors or home devices, but in reality, it seems to be covering just about every industry in general, like automotive, industrial, even medical in these times. And when it comes to using ARM in these industries, what would you say has been the biggest challenge that engineers have faced?
Well, that's an interesting question. I think, a developer challenge often is very specific to the environment that they're operating in. And, one of the areas that we're spending, we're always looking forward. So a lot of the time we're spending at the moment is looking at what are the challenges developers are facing to adopt modern AI technologies into the space of IoT. And, AI, I think everyone has considered as being large language models and in the cloud and, are familiar through the sort of chat GPT world, but actually AI is incredibly valuable and applicable at the edge. And actually there's a number of reasons that developers want to put AI into edge devices. Firstly, there's a sort of some real-time issues. If you're doing anything real-time, you don't want to be sending it off to a query in chat GPT and waiting for a return. So for that sort of latency and then the robustness, I can't guarantee I've got a really high bandwidth link to the cloud. Financial cost is another. We are not in a world where we can afford to run every query in the cloud and everybody have a sort of premium subscription to use these large models at scale. And then, the other thing that I find fascinating is just the innovation that it's providing, allowing people to do new things at the edge that perhaps they hadn't done before. So historically, sensing at the edge was a lot of the time, we were getting into MEMS and accelerometers and things like this. But, all of a sudden, AI has opened up things like video as a more useful sensor now that you can use. So, rather than having, switch-based light gates that have to be positioned everywhere, you can just have a camera and decide flexibly where the boundaries are and use people detection algorithms to work out when a threshold has been crossed. So it's allowing new use cases or different ways of solving problems that are more flexible. So all of those things are interesting, but they also have unique specific challenges dependent on the market. So if you're somebody building a video doorbell, getting the power envelope and the cost envelope that's going to fit something that somebody will pay for and stick on their front door presents some unique challenges that we have to provide the tools and the base technology to help them solve. So, they can't afford a big GPU to stick to the front door. They need to find a way of making this fit. So, understanding these trade-offs in the new world of AI, I think, is a new challenge for developers in all of those markets. And it's one where we're focused on really trying to help them apply AI in their different segments. So different challenges in different areas, but some fundamentals around adopting a new technology that really are sort of stretching developer thinking.
One problem that I've personally found with AI is I think because it's still in its youth, it's still a developing industry. It's nowhere near established in the way that other industries are. So we've got a lot of development on its way, and I have personally found that because of that, there's a lot of standards out there. Things change quite quickly. Libraries change, toolkits change, the way that computation's changed. And I have found that it makes older hardware more unusable faster. I find that it can be difficult to move code constantly as people change. Is this something that you think ARM has faced challenges with in terms of your process design? Because I'm guessing if you design like an NPU or some kind of inference engine that's going to accelerate it, you have to think about how that data is going to go in and out. And if it changes because someone's changed the way that things work in the future, that hardware can no longer be used.
Yeah. I think you've hit on something very clear there. I mean, I think I've already said my team, I feel, have to work 5 years in the future. They have to do what is coming, because we know that anything we develop will take time from what we deliver as technology to be realized in silicon, and then for that silicon to go to a a customer or a developer who's going to build with it, who then have to get their product to market. So, we've got to think about what is the problem and what are the techniques we're going to need to run in 5 years' time. I feel we're doing okay. And there's two reasons we've done okay in this space. One is we focused on the CPU first. So in all of the systems you develop for, there's a central processing unit. And the first thing we've been able to do is make that processor better at doing AI tasks. So not taking away any of its existing capabilities or capacity, but adding vector instructions that accelerate its ability to do matrix type maths. And now this isn't as fully optimized as a neural processor that you offload a complete task to and leave. It does also mean that you can get, a 2 to 4x improvement in running an AI algorithm just by using a newer CPU from ARM. So we have launched a range of these, our sort of M55 and M85 processors that have vector instruction enhancements that allow you to accelerate with something called helium instructions so that you get better performance just running on the CPU for these modern tasks. And because it's CPU led, it's not so hardware optimized that it doesn't have flexibility. So we do a lot of work in writing libraries of software that just mean that a compiler can do a pretty good job of getting you that performance from the CPU. So that's the first one. The second one that you mentioned there is neural processors or accelerators. And there's no doubt in my mind that AI is well suited to this heterogeneous, we call it, this sort of different types of compute for different purposes. And if you are doing something constantly with relatively high bandwidth, say looking for people in a video scene, it is worth offloading that to a specialist processor that can do a lot of matrix maths. But as the point you pointed out, the game changed quite radically. If I roll back 3-4 years, everybody was using convolutional networks and that was the future. And then all of a sudden along comes transformer models and algorithms like flash attention, and they need a completely different architecture. And so we were aware of this coming. Thankfully, we launched our Ethos Micro NPU, which was our embedded accelerator for these kind of products. And initially that was CNN optimized. And then we came out with our U85, our latest generation, just at the point that transformers were coming in. So the newest silicon that's coming out today has hardware optimizations which give you a further significant improvement in AI execution when you're running a transformer-based model in one of those end devices. So, we've had to think forward. We've had to be ready for that. But so far, I'm pleased to say we're sort of hopefully keeping pace with it, and hopefully as much as possible also making that a little abstracted for the user so they can still make progress with their development.
But I suspect that your industry, when it comes to AI inference, is going to be a bit less volatile than maybe like the large language model industries, where when they make transformations, they are quite groundbreaking, fundamental. But for IoT devices, like you said, because you can target a CPU and for 2 to 4 times performance increase, like you said. Because it's a CPU and it's able to take any kind of instruction, you could make converters, libraries, backward compatibility systems, so that if you target a different CPU that's slightly older, it will run. It may not be as fast, but it will still run. Unlike if you had a dedicated inference engine that simply could not even accept the instruction in the first place. Yeah,
that's absolutely true, and we've put quite a bit of work into that in our whole CPU business. So we recognise that the best engine in the world today to run inference is actually a CPU. Now, that's not because it's the most optimal, it's because it's the thing that you have in your device and in your developer toolkit. And so we've built a series of libraries we call ARM Clyde, which heavily deployed now in mobile and Android-based devices, but also we've brought them over to IoT as well, so that Linux developers, when they want to run inference on a CPU, they can get a significant improvement. So, just peer-to-peer, just taking that Clyde library, we can give you a 70% performance improvement of your AI algorithm just in the hard work we've done in the library to accelerate the instructions, making the best use of the CPU that is there. So we do the work to make people effective now, as well as thinking about can we make them even more effective in the future with further acceleration.
And do you think that might mean that sort of in the next sort of few years that IoT microcontrollers, especially based around ARM, might focus more on multi-core as opposed to trying to put in NPUs that may or may not be still usable? Like, if from what you've said, if I was an engineer, I might be more comfortable with maybe 6 ARM cores where I can dedicate 3 of them to inference, knowing that even if the model changes, it could still sort of run it.
That's an interesting one. I think we see a bit of what you're saying. But also see people wanting the dedicated hardware as well. So everyone wants the best of both, right? So
yes, they do.
Sometimes they want to run something incredibly efficiently, and they want that accelerator. So Ethos-U and U85 are getting really popular. The other piece you mentioned about multi-core is interesting. We do see multi-core in microcontrollers, and you'll see people with an M85 and an M55, or maybe a dual M33 in their product ranges. Often that's sort of software separation. So you might run the communication stack on one, and you might run your sensing and algorithms on the other. And sometimes you'll see M55, M85, and an Ethos-U 55 all in one product, where you've also got the accelerator to hand. But the other trend you mentioned about multi-core is interesting, because we are seeing a really interesting bridge between the world of the microcontroller embedded developer who thinks very much about a real-time operating system and a single core that they're targeting, bridging into people who are looking in the world of AI for more flexible and capable systems. And so we've seen a real push for the use of embedded Linux, actually, in IoT increasingly. And the use of higher-level programming languages and Python, which may be less efficient but give you a great deal more flexibility and ease of development and programming.
I will have to interrupt you very, very slightly, and this will be more, and this is going to be more of a message to the audience, because I do get irate when I see people dunking on Python. Right. Yes, it may not be the most efficient language, right? And I appreciate that you can do a for loop in C 1,000,000 times faster, but I've never seen a programming environment where I could develop something so fast and have it and effectively not have it crash, not have issues. It runs on any target that can run Python. You've got 1 billion libraries to use of the thing. And if like for example, if you want to do inference, you can import transformers from Hugging Face library. It's straight there. Download the files. It's straight there. No messing, no complaining, no compilation issues. So and like you say, people are going to say, oh, you can't put this on a microcontroller because it's too big and slow. The truth is, I'm already using MicroPython on microcontrollers because it's such a beautiful language to use.
Yeah, and I think that is part of what we're seeing. We're seeing people use it both in microcontrollers, but we're also seeing a desire to use it and have even more flexibility, particularly the point you make around just pulling in libraries. If I'm wanting to deal with a video stream and apply an AI algorithm to it, it is very straightforward and beautiful, as you said, to pull in those libraries and execute them. And so we actually launched a new IoT subsystem at the heart of which was a brand new A-class core designed explicitly for this purpose. It was a new product that brings the sort of power of Linux and AI sort of into the smaller form factor and the lower power envelope. It's a processor core called Cortex-A 320, and it's been designed from the ground up specifically for IoT type devices. So it is this hybrid. You can take it and you can run a single core of it and run a real-time operating system, and you can still code it in C and be very optimal. Equally, you can have 4 of the cores in a multi-core system, and you can run embedded Linux on it, and you can pull in libraries and do lots of flexible things. So we're helping developers bridge this sort of emerging trend and this divide between sweating every ounce of performance out of a deeply embedded platform and the flexibility and joy and pace of innovation you get with, coding in Python, frankly, and using PyTorch for your AI. So it was a really nice opportunity to bring those two things together in the Edge AI platform, and having that, very small, efficient A-class core coupled with an Ethos-U 85 accelerator. And then you've got, frankly, the best of both worlds with extreme flexibility in the programming model. So we definitely see that as a future trend that we think will be exciting for developers. It's
quite interesting you mentioned about embedded Linux, because And when I'm seeing this with microcontrollers, because as time progresses, the core speeds increase, the core counts increase, the memory increases. It's getting to the point where these microcontrollers are more powerful than a lot of personal computers from about 30 years ago. And I'm sort of wondering, do you think there might be a sort of time in the future where the line between what is considered a personal machine or a personal computer and an IoT device or a microcontroller becomes so ambiguous and vague that they might as well be the same thing?
So it's an interesting question, this. So at the other end of the spectrum, while we're seeing microcontroller software development get ever more complex and people wanting richer, more capable microcontroller systems bleeding into this world of microprocessors and sort of crossing that world into Linux, at the upper end of the developer cycle. So if I take the other end of the sort of IoT market where we've got, robotics and vision systems, the push for single thread performance and high speed execution is only getting bigger. So those things are looking ever more complex. Now, the thing that I feel is increasingly common, even if the systems are all pushing up for their performance and complexity, is the developer mindset. So we are seeing people ask for, virtualization down onto an embedded device so they can actually distribute a container-based...
Virtualization?
Yeah, so, at least...
Sorry, virtualization on a microcontroller?
Not on a microcontroller. So
but like small embedded systems?
But on systems, embedded systems, thinking, okay, I would like to be able to manage my code deployment and distribution in a factory or an embedded system that takes the same sort of principles as I have in the cloud to manage them. So rather than having very bespoke binary libraries that are burnt once for a device, having, like I described the light gates on a factory floor. Imagine you want to reconfigure that factory every 6 months. Well, let's put in a range of cameras that run Linux, and let's be able to distribute a new sort of image effectively in a container to that Linux-based camera periodically that redefines the functions of the factory floor. And then a camera can be light gates and people detection, or the next month it can be defect monitoring or things like this. So, these more flexible systems offer some real innovation opportunities in areas like automation, manufacturing, and distribution logistics that mean we are seeing people take more complex programming models into the sort of embedded and IoT space that look a lot more like what you might have thought of as very high performance, PC-like systems in the past. So,
for me, this sounds very much like software-defined hardware almost.
Yeah, I mean, and I think AI unlocks a bit of that. The ability to, take a complex sensor like video and deploy different algorithms for it to do different things dynamically is a really interesting potential inflection point for the way developers approach creating new systems. But, this is at the leading edge of innovation, and, there are still very much and always will be a place for the really power optimized thing for doing, we're not going to replace our TV remote control with a virtualized Linux system. So
who knows? Well, you don't know. You never know.
Maybe
right now, remote controls have microphones.
True.
It's real-time audio monitoring.
Yeah. Who knows? Someone may come up with something incredibly innovative that disrupts the space, but I think there will always be a place for that sort of power optimized thing. So
yeah.
we have to stretch to cover the two.
But do you not find that as people are wanting or have a requirement for greater and greater power efficiencies and smaller power envelopes, but then at the same time they're asking for all these new features, and you're kind of like, well, we can't give you both. We have to trade one for the other. Do you not find that it's becoming more of a problem these days?
I think it is a challenge for the developer to make that choice, and I get the luxury position of being able to step back and not be the developer in the moment, having to think about it. But it's often a trade-off of economics. So as I described, you can have that camera in a factory environment, and you can afford for that to be a premium plugged-in thing with that general flexibility because of the economics of that environment and the investment you're making. At the other end of the spectrum, not every market can afford that level of flexibility. Yeah. And so there is a need for both. And I generally find the trade-off between innovation, flexibility, and the ability to change and innovate is often something that you have to trade off against optimization, because I can get more optimized and I can squeeze power out and I can tune down software to a more compressed form. But it's going to cost me time. It's going to reduce my
Yeah.
flexibility.
But then again, that kind of comes back to the conversation about Python. If you make these sort of embedded systems so bloody powerful and so
Yes.
memory capable, it gets to the point where you say, well, I could spend 6 months developing the world's most beautiful piece of C code, or I could get this whacked out in an afternoon, just write the Python code, get it all sorted out, and deploy. And you'd also have the sort of like the safety around that, because those kind of interpreted languages tend to have like memory collection and sort of like safer guards around how these things operate. So it kind of makes you wonder if engineers are really looking to get things out quickly, bigger systems with more memory and more CPU capability could allow for those kind of languages to run.
Yeah, absolutely. And actually, that's been a cool part. I mentioned that sort of Cortex-A 320 in our Edge IoT platform. It's based on our V9 architecture, and it does implement those key security features that we built for mobile phones and Linux-based platforms. So you do get things like pointer authentication, target and branch identifiers, and you get memory tagging that do these things in the background to protect against memory safety issues in systems. So actually, by adopting these more arguably complex systems, you, as you say, and basing on standard operating systems that have embraced that V9 technology, you are getting some of those protections provided for you without you having to manually go and develop those in a microcontroller.
And you'd even go as far as that you could have operating systems like Linux, like Windows, which themselves have things like antivirus tools. They can check for unusual execution of code, and you can have these things running at the same time as your code is executing. So let's say you've got one sort of application, or two applications that come to my mind might be something like robotics or automotive. So let's say you've got a self-driving car. I already know that companies are actually deploying hypervisors in these things, so that different parts of the car, if they crash, they don't crash the entire system. But then in that same system, you might then want an operating system that actually has these tools to look for unusual code activity to make sure that they remain safe.
Yeah, no, I think what we certainly do see that both in the automotive space and the industrial space. You get these system level choices to put in effectively safety monitoring systems alongside your core code. So you can have it may be running actually on either a separate microcontroller or on a subsystem within a more complex chip that is doing let's make sure I don't go out of the bounds of any control environment that I'm in, at the same time as running a very rich, maybe even virtualized environment for the core application code for the vision system. So yeah, we're seeing a real fusion of that capability. But yeah, we've been very keen in the sort of new platforms to make sure that with ARM v9 and with what we're doing with our Ethos accelerator together, we're providing that flexibility, but bringing it to a cost and power envelope that is closer to the world of microcontroller. So building something very optimized for the IoT market. So reflecting that this coming trend is going to bring in a sort of new class of devices, which we think marries with what we hear from developers as to what they'd like to be working with.
And I would argue that reducing power envelope and energy consumption is going to be key to giving people those more powerful devices, because, as you say, in the industry of IoT, even if you want something super duper complex, usually power is constrained.
Yeah. Now, and the other point you made as well, which is fascinating, is the memory question. So as we use AI at the edge, the demands on memory are getting very large. These models, even though we're now in these small language models that are sort of 1 to 2 billion parameters, they take up a lot of memory, and copying that memory to live memory and then navigating through it to get your answers or process a video stream is memory intensive, very memory intensive. So we not only need ARM to innovate in providing these new cores like the A320, but also our partners choosing to adopt more modern process technology and bring in large memory sets to work with it, which allows you to execute these small language models in embedded devices at the edge.
And I might be overstepping my expertise here, because I'm not quite sure how this part works, but I'm guessing that this is where things like vectorized memory might be important, where you can access multiple banks at once to then push through sort of larger cores which can handle n number of streams or whatever, so they can do parallel operations.
One of the things that we definitely see is, with things like Cortex-A 320, people using, DDR memories to allow them to have much larger addressable banks of memory, so they can do that high-speed sort of streaming through a larger model. So Whereas, in the MCU world, it's typically SRAM and you're somewhat limited. By moving to a DDR architecture around an A-class core, you can expand dynamically into much larger memory set, a larger management.
And I do feel that the memory size of microcontrollers have gone from 8 kilobytes of static RAM all the way to like now they're over a megabyte, and then they're going to get bigger and bigger and bigger. But that's actually an interesting question, because what I'd like to ask is, why is it that we haven't seen more? Why don't we see DDR being used typically more in microcontrollers? What is it about it that makes it hard to implement?
So the nice thing about SRAMs and flash memories and some of the MRAMs that are available is that they can be implemented in the process of laying down the chip for the microcontroller. And so within the footprint of the SoC itself, you can put down on the same process node, say historically 40 nanometer, you could lay down a flash block and a number of SRAM blocks and have a single die and produce a relatively low-cost system. DDR typically produced in a much different process.
Seriously?
Memory process, and not something you can synthesize directly on the same.
I had no idea. I always assumed DDR was like the same kind of technology as CMOS process nodes would use. Is it not?
Well, typically the memory providers actually have their own fabrication facilities using different processes. So it's not something you include in the floor plan of the same process and design. And therefore you typically have to have a physical interface to move off chip to then address the DDR memory, which will be provided by a memory provider in a completely different process.
And so basically DRAM is it's so different that you. Do you know what? I never even realised. I always assumed it was because I know it's basically a transistor and a capacitor, but I just assumed it would be like, I don't know, an NMOS transistor or something stuck to a capacitor. But if it really is that different, you're just saying you can't even integrate it onto the same wafer.
Well, there's always these debates, and you could try and take processing into memory technologies and fabricate it on the same node. But where you look at the way that processor development is created versus the specific requirements of developing large memories, there isn't a nice fusion of the two. So you typically then split apart into having a DDR-based memory and a integrated microprocessor unit, which has a DDR physical interface to allow you to connect.
And then you'll have to wire bond them together for them to work together.
Yeah, exactly. And you can either have them stacked in package, or you can have separate devices on the PCB to achieve that. But it does allow you to have much more flexibility and scalability in the memory that you create.
Now, looking forward to the next 5 years, because you mentioned yourself that one of the biggest challenges that you guys face at ARM is that you have to keep trying to anticipate what people are going to do to make hardware that's going to last and be viable and valuable for the next sort of 5 years. What do you think is going to change in the next 5 years, and what are you doing to account for that?
So I suppose one of the biggest trends, it comes back to this question of ever-increasing compute need, and I think, AI really sort of changing a bit the paradigm in that development of algorithms that are going to be deployed. And I saw a quote from, I think it was Sam Altman, talking about, in the world of cloud AI, he's encouraging people to basically build on the existing large models that are there, because he's saying the rate of improvement in the large models is so fast that if you try to over-optimize the large models, by the time you've optimized it, there'll be a new, better one around.
Yeah.
And I think that's an interesting challenge we see, is that, large models are allowing us to do new innovative things, even helping us write our code, for example, to target these devices or create and train, distilled models that can then be run on edge devices. And so that looks like it's coming, and therefore architectures that allow you to align to and deploy the output of cloud-based AI are going to become more valuable. So I think, Ethos-U 85, our transformer-based micro NPU for the edge, was really well timed, because transformers hit at the right time, and that is the architecture that is really driving all of the innovation in cloud. So being able to take that and execute it well at the edge has been really important. And I think similarly, as we look forward for ARM, we're looking at how do we make sure that the edge keeps pace with what is happening in the cloud. How can you make sure that as those models evolve and get better and more capable, you can deploy that capability at the edge and you can do it securely. So we're very focused on that sort of translatability from developers training and developing in the cloud to being able to deploy on edge devices. And it, as you pointed out, there may be a number of disruptions along the way, but the pace of change is like almost nothing I've seen in sort of 30 years in the industry in terms of the rate of growth there.
Fantastic. So just before we wrap up this video, I've got one more question for you. For the audience who are watching this video, if they want to get involved with ARM solutions, what would you recommend that they do?
Oh, wow. So all depends on what you're doing. I mean, as I said, 20 billion devices a year going out based on ARM in my team.
Let's go IoT. What should they do if they're involved in IoT?
IoT, yeah. So for IoT in that space, I mean, if you're a developer who's sort of wanting to experiment and use the latest in AI, I would say, look out for the microprocessors, and microcontrollers that are using Helium instructions from ARM, so M55, M85, and the tooling we've provided around being able to deploy onto those devices. And then look out for Ethos-U. If you want to optimize and accelerate your algorithm, whether it's sort of Infineon or Aleph, there's a number of vendors coming out with Ethos-U based accelerators on board, and you'll be able to see that more than 10x improvement in your algorithms. So experimenting in there with the new dev kits that are coming out from those guys, I think is a great place to sort of stretch where your sort of experience of AI at the edge is going.
Absolutely fantastic. Thank you ever so much for being here today.
Real pleasure. Thanks very much.
Thank you.